Let's jump right into today's explainer, which is basically a dynamic, hands-on workshop to completely demystify the 2D Cartesian coordinate system. If you've ever looked at a graph or a map and thought it was just this random scatter of numbers and lines, well, we're going to change that right now. We're going to build a really structured visual understanding of exactly how we map our physical reality. Okay, here's our quick roadmap for today. First, welcome to the grid. Then, finding the distance. Third, locating the midpoint. 4, formula in action. 5, step-by-step practice. And finally, number 6, a pop quiz and review. Let's get into it. Kicking things off with Section 1, welcome to the grid. Now, to really understand abstract math, we first have to ground it in reality, right? In our source story, there's a boy named Rian who's moving to a new house, and he happens to be visually impaired. His sister Shalene did something completely ingenious. She used pins and strings on a grid to help him actually feel the layout of his new room. By using a horizontal x-axis and a vertical y-axis, she basically created a perfect physical model of the 2D Cartesian plane. It's super cool because it allowed Rian to navigate his space with absolute pinpoint accuracy. But hey, every map needs a starting point, right? And in the 2D coordinate system, that starting point is called the origin, which sits right at the coordinates 0, 0. And as our source material fascinatingly points out, this starting point literally owes its existence to the ancient mathematician Brahmagupta. It was his formalization of 0 that made the 4-quadrant Cartesian plane we use today entirely possible. Pretty amazing history there. So here is the absolutely crucial takeaway. To plot any point, let's just call it x, y, you only need to follow 2 foolproof steps. First, you move along the horizontal x-axis. Think of that like walking across the floor. Second, you move along the vertical y-axis, which is kind of like climbing a ladder. So walk first, climb second. Always, always in that order. Moving right along to Section 2, finding the distance. Okay, so we know how to plot points, but what happens when we actually need to measure the distance between 2 points that aren't sitting on a neat, straight, horizontal or vertical line? Well, instead of just blindly memorizing some long formula, I want you to really visualize it. Whenever you have a slanted line on your grid, you can literally draw a right-angled triangle right around it. The horizontal distance between your points becomes the base, and the vertical distance becomes the height. And as our source notes, this totally leverages the ancient Pythagoras theorem, magically turning coordinate distance into simple triangle geometry.
All right, Section 3, locating the midpoint.
Now that we know exactly how to visualize the total distance between 2 points, how do we find the exact middle of that line? Well, finding the midpoint is brilliantly simple. You're basically just calculating an average. You take the average of the 2 x coordinates to find the middle horizontally, and then you take the average of the 2 y coordinates to find the middle vertically. Combine those 2 averages, and boom, you have your exact center point. That brings us to Section 4, formula in action. Okay, let's actually put this distance formula into action and see exactly how the math plays out. I want you to try and mentally picture the points we're looking at. We've got point A at 3, 4, and point D at 7, 1. So ask yourself, how much horizontal distance is covered along the x-axis between 3 and 7, and how much vertical distance along the y-axis between 4 and 1? And this perfectly illustrates the formula at work. Let's break it down. We find the horizontal difference, which is 4. Then we find the vertical difference, which is -3. We square both of those numbers to get 16 and 9. Add them together, you get 25. And finally, you just take the square root of that, which gives us exactly 5 units of distance. See? It's literally just finding the hypotenuse of a right-angled triangle. Easy, right? Up next is Section 5, step-by-step practice. You've seen how I do it with the distance formula, so now let's shift gears. We're going to rapid-fire solve 4 more questions together just to make this second nature. Let's go back to Rage Onion's room from our source story. Think about the physical properties of a rectangle on a strict coordinate grid. The sides absolutely must be perfectly horizontal and vertical. So if his rectangular table has 3 feet already plotted, and we align the remaining x and y coordinates from those feet, where exactly does that 4th pin need to drop? If you guessed 8, 7, you hit the nail on the head. By simply matching the x-coordinate of the first point, which is 8, and the y-coordinate of the third point, which is 7, we effortlessly lock in that final corner. So the 4th foot has to go at 8, 7 to complete the rectangle. All right, question 3. Let's pull out that midpoint step-by-step guide we went over earlier. We need to find the exact center between point A at 4, 7 and point B at 16, -2. Think about it. What is the average of 4 and 16? And what's the average of 7 and -2? Let's just do it step by step. We average the values. 4 plus 16 is 20, divide that by 2, and you get 10. Then 7 plus -2 is 5, divide that by 2, and you get 2.5. Put them together, and we find our perfect center balance right at the coordinates 10, 2.5. Moving on to question 4. Now this one looks pretty intimidating right out of the gate with 4 different points. But you already have the tool to solve it. It's the distance formula. How do we actually prove a shape is a perfect square? Well, all 4 sides must be exactly the same length, right? So, by running our trusty distance formula on all 4 sides, calculating the differences, squaring them, and adding them up, we find that every single side equals the square root of 10. Since they're all identical, we've proven geometrically, without a shadow of a doubt, that this shape is indeed a square. No way around it. Okay, question 5. And this is a really fascinating challenge directly from the text. Without even plotting these points on a piece of graph paper, how can the distance formula alone prove that these 3 points form a perfectly straight path? Any ideas? Well, here is a beautiful little trick in coordinate geometry. First, we find the distance of the smaller segment MA, which is 5 units. Then the distance of segment AG is 10 units. Finally, we calculate the total distance from M all the way to G, and that comes out to 15 units. Because the 2 smaller segments perfectly add up to the total longest segment, 5 plus 10 equals 15, they must, by definition, lie flat on a perfectly straight line. Isn't that clever? And finally, section 6, pop quiz and review. You guys have done incredible work. You've plotted points, calculated midpoints, and totally mastered the distance formula. So let's wrap this whole explainer up with a quick pop quiz to test those newly minted coordinate skills. We all know that point 2, 5 is in a very different location from point 5, 2 on the grid. But if you plug those coordinates into the distance formula completely backwards, does it break the math? Like, does order actually matter for distance? The answer is a resounding no. And here's why. Because we square the differences in the distance formula, any negative signs completely vanish. That means the order of the points literally doesn't matter at all for finding the final distance. To leave you with a final thought from our source material today, coordinate geometry has mapped our world for thousands of years. We're talking from ancient city street grids all the way to the GPS in your phone right now. It is the hidden code of our reality. So, armed with these tools, what will you map next?